Okay, I want you to picture the most complex machine you can possibly imagine.
Right.
Like a supercomputer running a simulation of the entire human brain. Or a library with every single book ever written inside.
Okay, I'm picturing it, just immense, immense scale.
Now, if I told you that I wanted to teach that massive system a completely new, high-level skill, like how to solve advanced calculus problems, or maybe reason through a really tough logic puzzle, what would you assume that takes?
Well, the standard assumption is it takes math.
Right.
It takes data. You'd need to feed it thousands of textbooks, run it through, I don't know, millions of practice problems.
We're adding new wings to the library.
You're adding information in to get capability out. That's been the dogma. Scale is everything.
But what if I told you that is just completely wrong? What if I told you that you could take one of these huge AI models, an 8 billion parameter giant, and teach it to solve complex reasoning problems using a file that is smaller than a single tweet?
That sounds like a magic trick.
It does.
Or, I mean, frankly, a scam.
It sounds physically impossible. I'm looking at the notes here, and I see the number, but I'm really struggling to believe it. We're talking about a paper that just dropped on arXiv called Learning to Reason in 13 Parameters.
It's a wild title, I'll give you that. But after reading through the work from the authors, John X. Morris, Nilüfer Mareshkala, and their team, it's not a scam. It's a fundamental challenge to how we think AI even learns.
So that's our mission for this deep dive.
Yeah.
We need to unpack what they did with this method they call TinyLoRA. Because the claim is that they unlocked high-level reasoning using, and I am not joking here, 26 bytes of data.
26 bytes.
Okay, stop. We have to pause on that number. 26 bytes. An 8 billion parameter model is what, 15, 16 gigabytes?
In that ballpark, yeah.
And you're telling me that a file size of 26 bytes, which is, what is that, a string of 13 characters, can actually change how that entire brain thinks?
That sounds like a rounding error, doesn't it?
It sounds like nothing. If I change 26 bytes in a Word doc, I fix a typo. I don't rewrite the entire plot of the novel. How can this possibly work?
That is the million-dollar question. And to answer it, we really have to look under the hood of how these models are normally trained, because this paper suggests we've been thinking about learning all wrong.
Okay, so let's back up. Before we get to the tiny part, let's just establish the baseline. You mentioned the dogma. How do we normally teach a model new tricks?
Well, the old gold standard was full fine-tuning. You take the model, all 8 billion parameters, and you slightly adjust every single one of them with new data.
Which is just incredibly expensive.
Prohibitively expensive for most people, yeah. You need a supercomputer cluster just to run one update. So the industry moved to something called LoRA.
LoRA. Okay, I've heard this term a lot. It stands for Low-Rank Adaptation.
Correct. And this is where we need to get a little bit visual. So imagine the model's brain is a massive, dense cube of numbers. To teach it something new using standard LoRA, we don't touch that cube. Instead, we kind of inject two new, much smaller grids matrices into the layers.
Right, so instead of rewiring the entire building, we're just adding a little extension cord to the fuse box.
That's a perfect analogy. You freeze the main brain and just train these little side matrices. It's much, much more efficient. But here's the problem the authors found. Even that extension cord is still pretty heavy.
Heavy how?
In standard LoRA, you're still dealing with matrices, grids of numbers. And even if you make them small, they have to match the dimensions of the model. So you're still training thousands, sometimes millions of parameters.
So even the light version is still kind of heavy.
Relative to what we're about to discuss, yes, it's massive. Standard LoRA has a floor. You can only make a grid so small before it stops being a grid.
And that's where this paper comes in.
That's where it comes in. They ask this really radical question. Do we really need a grid? Do we even need a matrix at all?
And the answer was no.
The answer was a resounding no. They realized that for certain tasks, especially reasoning, the intrinsic dimension, the actual space you need to solve the problem, is virtually zero. It's not a grid, it's a point.
And this is TinyLoRA.
This is TinyLoRA. It's their method for scaling these adapters all the way down to sizes as small as one single parameter.
One parameter out of 8 billion.
One.
Okay, so the analogy that's jumping into my head is, imagine you have a giant circuit breaker panel. Thousands of switches controlling a whole city.
Okay, yeah.
The old way was rewiring the whole panel. Standard LoRA was like walking up and flipping a whole row of switches at once. TinyLoRA is like walking up to that massive panel, finding one specific single switch and just nudging it.
That's a great way to visualize it, but I might even take it a step further. It's not just nudging a switch, it's like inserting a tiny shim that slightly changes the angle of one single mirror in a giant telescope.
Wow.
And suddenly the entire image just snaps into focus.
But the assumption has always been that just changing one mirror wouldn't do anything, that the system's too complex. We thought you had to adjust the whole flow of information.
We did. We thought intelligence required bandwidth. But these researchers just said, let's test that. Let's see if we can teach a model to reason, a really high-level task, by barely touching it.
Okay, let's get into the experiment itself. I'm still skeptical about these results. You can have a great theory,
Yeah.
but did it actually work?
The setup was pretty rigorous.
Yeah.
They used a model called Quinn 2.5, specifically the 8 billion parameter version,
Yeah.
a very capable open-weight model.
And they tested it on GSM-8K. I see this acronym all the time.
All the time.
It stands for grade school math, right? But that sounds too easy.
It does, but don't let the name fool you.
Yeah, grade school math sounds like, multiplication table.
It's not. These are tricky multi-step word problems. You know the type. If a train leaves Chicago going 60 miles per hour and a bird flies,
Right.
it requires real reasoning. You have to read it, formulate a plan, do the steps. If you mess up step one, the whole thing falls apart.
So it's a test of logical consistency, not just calculation.
Exactly. It's a gold standard for testing if an AI can actually think through a problem.
Okay, so they take this 8 billion parameter beast, they apply their TinyLoRA method, and what happened?
The model achieved 91% accuracy on GSM-8K.
91%. That's A-grade performance.
It's exceptional. It rivals models that have been fine-tuned on huge data sets, but the accuracy isn't the headline.
No?
The headline is the cost. To get that 91% accuracy, they only trained 13 parameters.
13.
Yeah.
Not 13 million, not 13,000, 13.
Just 13.
And this is where that 26-byte figure comes from, right?
Yeah.
I just want to make sure I understand the math.
Right, let's break it down. So the parameters are stored in a format called BF16, bfloat16. It's just how computers represent numbers.
Okay.
And each parameter in BF16 takes up exactly 2 bytes of memory.
So 13 parameters times 2 bytes each.
Is 26 bytes.
26 total bytes.
Uh-huh.
I want to put that in perspective for everyone listening. An empty text file on your computer is often bigger than 26 bytes, just from the metadata.
Oh, yeah.
The icon for this podcast app on your phone is probably 50,000 times larger than that file.
You could write the code for this entire reasoning brain on a single Post-it note.
It's absurd. It feels absurd. We're controlling an 8 billion parameter superbrain with a Post-it note.
It really challenges our whole intuition. We equate learning with acquiring mass, right? Adding more books to the library. This suggests that for these models, learning to reason isn't about adding mass at all.
Now, I know what some listeners are thinking, because I'm thinking it. Okay, maybe they got lucky. A fluke with this one math test.
And the researchers knew people would say that. They didn't stop at GSM-8K. They ran this against a whole suite of much harder benchmarks, like AIME and MATH500.
AIME, that's the American Invitational Mathematics Examination. That's for high school mathletes. That's serious stuff.
It's very hard. And the trend held. Across the board, they recovered about 90% of the performance improvements you'd expect from a full, massive training run.
While using a tiny fraction of the parameter.
A tiny fraction. They were training 1,000 times fewer parameters than standard methods.
So you're getting 90% of the benefit for 1/1,000th of the cost.
That's the definition of efficiency.
Okay, but now we have to get to the how, because this is the part I found really surprising. You can't just go in there with a wrench and start twisting 13 random knobs, can you?
Oh, absolutely not. No. If you pick 13 random parameters and change them, you'd probably break the model, make it output gibberish.
Right.
The breakthrough relies entirely on how they found those parameters and how they trained them.
And this brings us to the big comparison in the paper, SFT versus RL.
Yes. This, in my opinion, is the most scientifically significant finding. They compared 2 training methods, Supervised Fine-Tuning, or SFT, and Reinforcement Learning, RL.
Let's break those down. SFT, that's basically the standard way we do things, isn't it?
It is. With Supervised Fine-Tuning, you show the model a question, and then you show it the perfect answer. You're saying, here's the input, here's the output, memorize this pattern.
It's like giving a student a textbook and saying, just memorize these facts.
Exactly. Reinforcement learning is totally different. RL is more like, here's a problem, go try to solve it. If you get it right, you get a reward. If you get it wrong, try something else.
So it's trial and error.
It's learning through exploration.
So SFT is memorizing.
Yeah.
RL is figuring it out.
Precisely.
Yeah.
Now here's the bombshell. When the researchers tried to use TinyLoRA with SFT, when they tried to just show the model the answers using only 13 parameters, it failed.
It didn't work at all.
It was useless. The capacity was just too small. To get the same performance with SFT, they needed updates that were 100 to 1,000 times larger.
Whoa. So the tiny method is physically impossible if you're using the standard memorize this technique.
Correct. But when they switched to reinforcement learning, when they let the model figure it out on its own, boom, they could hit that 91% accuracy with just those 13 parameters.
That's a huge difference. But why? Why does the method of teaching change the file size needed? Why does SFT need a whole library, but RL just needs a Post-it note?
This gets right to the heart of what reasoning actually is in these models. The authors argue that SFT is largely about pattern matching, memorization. And memorizing a huge variety of specific answers requires storage space. You need parameters to hold all those different templates. You're adding furniture to the room.
Right, you're trying to imprint a complex pattern onto the model. That takes bandwidth.
Exactly. But reinforcement learning, the researchers argue it's doing something fundamentally different. It's not adding furniture, it's just rearranging the furniture that's already in the room.
Rearranging?
Think about it. This 8 billion parameter model has already read the entire internet. It's seen every math textbook, every logic puzzle, every piece of code. The capability is already dormant inside it.
So the knowledge is already there, it's just messy.
Unorganized.
Or unconnected. The RL process isn't teaching the model how to add. The RL process is finding the specific neural pathway, the subspace, that leads to the right answer, and it's just reinforcing that path. It becomes an alignment problem.
That is a mind-bending concept. So the 13 parameters aren't the knowledge. They're just the signpost. That's the perfect analogy. The 26 bytes act as a steering vector. It just says, hey, for this problem, ignore the creative writing circuit, ignore the poetry circuit, and route all energy to the logic circuit over here.
You don't need megabytes of data to flip a switch.
You just need to know which switch to flip. And that's why SFT failed at this tiny size. You can't fit a library into 26 bytes.
But you can fit a key into 26 bytes.
Exactly. The SFT approach is trying to shove a new library through the front door. The RL approach is just sliding a key into a lock that was already there.
This makes me think about the future of how we deploy this stuff. Right now, the model is, well, it's monolithic. We have these giant models. But if this tiny LoRA thing holds up, that changes the logistics completely, doesn't it?
And it changes everything. It really points toward a much more modular future. Imagine you have your base AI model on your phone. You don't need to download a whole new multi-gigabyte model just to make it better at math. You just download the math skill patch.
And because it's 26 bytes, that download is instantaneous.
It's instant. You could literally email an upgrade to an AI. You could put it on a QR code. You could have a library of thousands of skills, a legal reasoning patch, a Python coding patch, a sourdough baking patch.
And you just swap them in and out of active memory as you need them?
Ideally, yes. It decouples the intelligence from the raw knowledge. It's just we can build these highly specialized, expert-level reasoning systems without needing expert-level compute clusters to train them.
It really is a less is more moment, isn't it? We've spent so much time focused on the 8 billion part of the 8 billion parameter model. And these researchers just walked in and said, hey, what about these 13 guys over here in the corner?
And it turns out those 13 guys are doing all the heavy lifting when it comes to logic. It's a powerful reminder that we still really don't understand the internal landscape of these networks.
So to just recap what we've unpacked today in this deep dive, we have an 8 billion parameter model. We have a team that used a method called TinyLoRA to train just 13 parameters, totaling 26 bytes of data.
Correct.
And by using reinforcement learning instead of standard supervised training, they got 91% accuracy on complex math problems, performing nearly as well as models trained with thousands of times more data.
A 26-byte key that unlocks 91% accuracy. It's just a remarkable efficiency breakthrough.
It really shifts the perspective. We usually think of AI progress as needing more power, more chips, more energy. This paper argues maybe we just need to be smarter about how we teach, not just how much we teach.
Absolutely. It moves us from an era of brute force to hopefully an era of precision.
I want to leave you, the listener, with one last thought to mull over. We talked about how reinforcement learning works like a key, right? Unlocking capabilities that were already dormant inside the model.
Sleeping giants, essentially.
Exactly. So if a massive AI brain already knows how to do advanced reasoning, and it just needs a tiny 26-byte code to wake that skill up, What else is sleeping in there?
That is the scary and exciting question.
What other profound capabilities, creative, analytical, maybe even things we don't have words for yet, are just sitting silently inside these models waiting for someone to find the right 13 parameters to turn them on?
We might be sitting on a gold mine of capabilities that we just haven't found the keys for yet.
Something to think about. Thanks for joining us on this deep dive.
My pleasure.
We'll see you next time.